Hey everyone, welcome. Today we're continuing to work on the brain teaser questions from the Green Book. So starting off with burning ropes. In this question we have 2 ropes, and each of which takes 1 hour to burn. But either rope has different densities at different points, so there's no guarantee of the consistency and time it takes different sections of the rope to burn. So how do you use these 2 ropes to measure 45 minutes? So we're given 2 ropes, but they have different densities. So we can't look at the rope and say, hey, it burned 75%, so that's 45 minutes. So the only way we actually can measure time with these ropes is if it burns to full, or like the entire rope is burned. So we want 45 minutes, and each rope burns for 1 hour. So 45 minutes is 75%. So an idea that pops into my head is that we need to split these ropes into sections of 4. However, we can't actually look at the rope and see like 1/4 of it is burned, so there has to be another way to split it into sections of 4. So something this question doesn't tell you, and something that is actually a big clue, is that ropes have 2 ends, and we can start burning the rope from both ends at the same time. So suppose we start burning one rope from 2 ends. So how long does it take for the fires to meet in the middle? Well, the rope takes 1 hour to burn from one end, so it's going to take half of that, or 30 minutes if we burn from both ends. So it's going to take 30 minutes if we light it from both ends. However, we're not looking for 30 minutes, we're looking for 45 minutes. So we need to measure 30 minutes and then half of 30 minutes. So is there a way to measure half of 30 minutes? Well, technically yes, because we can first measure 30 minutes. So we have one rope burn all the way to its end, and then we need another rope to have 30 minutes left, and then we can light it from both ends. So to have the other rope have 30 minutes left after the first 30 minutes has passed, then we should light the other rope from one end at the very start. So in this solution, after 30 minutes passes, 30 minutes passed, what do we have? The first rope, well, it's all burned, so there's nothing left in the first rope. The second rope, it's burning from one end, and there's 30 minutes left in its lifespan. So 30 minutes passed, we want to measure 45 minutes, so we want to measure 15 more minutes. So to measure 15 more minutes, well, we can conveniently light the second rope from the other end. So now both ends are burning at the second rope, and instead of having a lifespan of 30 minutes, because we lit it from the other half, it now has a lifespan of 15 minutes. So the 30 minutes that passes initially, plus the 15 minutes that we have left, add up to 45 minutes. So that's how we use 2 ropes to measure 45 minutes. Hopefully that made sense. This question skipped the part where it says the ropes have 2 ends to burn, but that's kind of inherent when we think of a rope. So the rope isn't a circle, it's a straight line, so we can start burning it from both ends. So moving on to the next question. Trailing zeros. So how many trailing zeros are there in 100 factorial? So 100 factorial, that's 100 times 99 times 98, and so on. And a trailing zero is the number of zeros at the end of a number. So if your number is 753000, then there's 3 trailing zeros. If our number is 0, there's no trailing zeros because there's no number in front of the 0. So with that out of the way, how do we solve this question? So for a trailing zero to form, we need a number to have a factor of 2 and a factor of 5, because 2 times 5 equals to 10, and that's what generates a trailing zero. So we can look at the powers of 2 and powers of 5 within 100 factorial to see how many powers of 10 we have, which is how many trailing zeros we have. So we know that there's lots more 2's than 5's in 100 factorial, because 2 is the number that is smaller, so more 2's will occur. So our bottleneck here is actually this power here. So how many 5's are there basically in the numbers from 1 to 100? So well, we have 5, 10, 15, 20, all the way to 100. So how many numbers are there? We have a gap of 5, so 100 divided by 5. This has 20 numbers. However, some of these numbers actually contain more than one 5. These numbers are, for example, 25, 50, 75, and 100. So instead of containing one 5, these numbers actually contain 2 5's. because they have 5 to the power of 2 within them. So we can have 20 numbers here and have 4 numbers that contain 2 5s. Are there numbers that contain 3 5s? For us to have 3 5s, we need 5 to the power of 3, which is 125. But 125 isn't in the range from 1 to 100, so it's not in 100 factorial, so we're never going to get any powers greater than 5 to the power of 2. So we have 4 numbers that have 2 5s, so 4 times 2, and 20 minus 4 numbers that have 1 5, so times 1. So we can cancel out this, so this plus this, we get a total of 24. So there's 24 5s in 100 factorial multiplying together. We know there's more than enough 2's, so that leads to 24 trailing zeros. So this question is pretty simple. We just have to find out the bottleneck is the number of 5s in the multiplication, and it's pretty simple to find how many 5s there are. So moving on to the next question, horse race. So this is a more interesting question. So this question says there are 25 horses, each of which runs at a constant speed that is different from the other horses. So every horse runs at the same constant speed no matter how we race them, and every horse has a different speed than the other horses. So we have a track that only has 5 lanes, so each race can only race at most 5 horses. Now we need to identify the fastest 3 horses, or the 3 fastest horses. So what's the minimum number of races needed to identify them? So for this question, right off the bat, we see that we want to find the 3 fastest horses. To know the fastest horses, I think we need to race all of the horses. Because if there's one horse that's left unraced, we don't know the speed of it. It could be the fastest horse. So knowing that we need to race all the horses, the most efficient way to race all the horses is to split them into 5 groups. Because we have 25 horses, so we can split into 5 groups of 5. So let's call that Group A, Group B, Group C, Group D, and Group E. So we have 5 groups, and each group has 5 horses. Let's call them A1, A2, A3, A4, A5, B1, B2. I'm not going to write all of them. So basically, the letter represents the group, and 1, 2, 3, 4, 5 represents the speed. So we need to race every group, so that takes us 1, 2, 3, 4, 5 races. We need 5 races right off the bat to determine the relative order of horses within a group. So let's call the fastest horse in a group the 1. So A1 is the fastest horse in group 1. A2 is the second fastest horse in group A, and so on. So now we have the relative orders, but we don't know which horses are the fastest 3. So to find the fastest horse, we can race the champions of each group. So basically, we can race the fastest horse in every single group. So we're going to race A1, B1, C1, D1, and E1. So we have one more race, the 6th race here, and what we're racing is A1, B1, C1, D1, and E1. E1, and this is the 6th race. So in this race, we determined that these 2 horses, D and E, these horses are guaranteed not to be the D1 and E1. These horses are guaranteed not to be the fastest 3 because we know that A1, B1, and C1 are faster than them. So right off the bat, we can eliminate D1 and E1. These horses are guaranteed not to be the fastest 3. Similarly, in each group, we can eliminate the last 2 horses because there's 3 horses in that group that are already faster than them. So the 4s and the 5s in every group should automatically be eliminated. So now we've eliminated the horses D1 and E1, as well as the bottom 2. So we know D1 is guaranteed to be faster than D2 and D3. E1 is guaranteed to be faster than E2 and E3. So knowing that we eliminated D1 and E1, we can also eliminate D2, D3, E2, E3. So now we eliminated a good chunk of horses from being the fastest ones. So what else can we eliminate? Well, we can actually eliminate more horses from groups B and C. So let's write that out first. So C1, C2, C3. So we can have C2 or C3 be the fastest horses because we know that there's already 3 horses, A1, B1, and C1. So even if C2 and C3 are the next horses, they have to go after C1 because we know that in group C, C1 is the fastest. So even if C2 and C3 are the next fastest horses, they're not going to make the top 3. So we can just eliminate C2 and C3. Similarly, we can also eliminate B2. So even if B2 is the next fastest horse, sorry, not B2, B3. So even if B2 and B3 are the fastest horses, they could be here. So B2 and B3. So we have A1, B1, B2, B3. So even if group B is the best group, B3 is not going to make the cut into the top 3. So similarly to how we eliminate C2 and C3, we can also eliminate B3. So now how many horses do we have? We have these horses that are highlighted in yellow that are potentially the top 3 horses. So that's 6 horses, A1, A2, A3, B1, B2, and C1. So we need the top 3 horses out of these. And also, I forgot to mention something, we know that A1 is guaranteed to be the fastest horse because it's the fastest horse in its group and it's the fastest horse in all the champions of the other groups. So A1 is the fastest horse and we know that for sure. So A1 is guaranteed to be the top 3. So now all we have to do is raise the candidates for the top 3 that are not A1. So the candidates remain A2, A3, B1, B2, and C1. So there's 5 horses, so we can do one more race. We host that A2, A3, B1, B2, and C1. So the top 2 horses here, A2 and A3, supposedly, it could be any of them. Those would be the fastest horses in combination with A1. Okay, use a different color. So let's use blue. So these horses, suppose this is the order, it could be any of the orders. So the 2 fastest horses in the 7th race and A1 will together form the 3 fastest horses. So one more thing I should mention is that I said the order of the groups is, of the champions race is A1, B1, C1, D1, E1. So this is not necessarily the case, but because all the horses are symmetrical at the start when we don't know their speeds, these labels are just labels we throw on the horses. If it was a different order, we can just swap the group names. So for example, if B1 was first, we could just swap B1 and A1 so that we always have the A being the winning horse. So without loss of generality, I just said A1 was the fastest, B1 was the second fastest, and then C1, D1, and E1, and so on. So that's this question. The question asked for what the minimum number of races we need to identify the fastest 3 horses, and we did 7 races to identify them. So our answer should be 7. So that's it for this question, and that's it for the video. So thank you guys so much for watching. Hope you're able to learn something, and I'll see you in the next video.